Sean is here. They have a presentation on learning empathy from a bug. Sean is a former Rails committer, and they now co-lead the team responsible for crates.io. That's the package repository for Rust, if you've never played with that. And then so I asked a few questions because, well, I'm quite old already, so I thought, well, how is that thing? Because this talk is about Pokemon Blue. Well, you can make mistakes, I've heard, but you can also do it really well. But I've learned that Pokemon is both singular and plural. So I've learned way better things today already, by the way. But this talk is heavy on
better than learning about Pokemon?
And heavy on Pokemon, plural. Sean, come in.
I was just saying, sorry, what's better than learning about Pokemon? All right. Hello, everybody. My name is Siân Griffin. I was hoping that there would be a Zubat emoji for y'all to spam in chat, but there isn't. So there will be a point. You will know when it is time. Here, you can see my Twitter handle on the slide. Please @ me with just all of the pictures of Zubats. I would appreciate that very much. Text encoding is really hard, so sometimes my name is spelled like this. My pronouns are they, them, and let's talk about Pokemon. The first Pokemon game was made by a small team for Japanese audiences. The game was made on a really tiny budget, and the programming team was only 4 people. In 1996, Pokemon Red and Green were released, and sales vastly exceeded expectations. Later that year, an updated version was released in Japan with improved graphics and more polish. After it was clear that this game was far more popular than anybody expected, there was a mad rush to localize it for international audiences. 2 years later, in 1998, Pokemon Red and Blue were released to the rest of the world and would go on to become the highest grossing media franchise of all time, eclipsing even Mickey Mouse and Hello Kitty. And even if you've never played Pokemon, I'll wager you've seen this one before. This is an actual picture of Ryan Reynolds from 1998. Okay, not really. This is Pikachu. By far the most famous Pokemon. But there was a close second. This is Missingno. Missingno is a glitch Pokemon, and you could only encounter this Pokemon through a glitch. But the thing is, everybody knew about it. One of the things I find most fascinating about this glitch is how widespread it was. In a survey I ran, 87% of people who owned the game knew about the glitch when it was still relevant. And about 80% of those people heard about it through word of mouth, not the internet. And there was a good reason so many people knew about this bug. Missingno could duplicate items. Now, the glitch had a lot of names. Some people called it the Missingno glitch. Some people called it the item dupe glitch. At my school, it was called the rare candy glitch, since most people used it to duplicate an item with that name. It made your Pokemon more powerful when you used it, so it was a really desirable item to duplicate. Let's take a look at how you perform the glitch. We start off in Viridian City, one of the earliest areas in the game. We're going to talk to this old man, and we'll tell him that we're not in a hurry. Oh. We're really not in a hurry because I did that slide transition too early. He will then take us into a tutorial where he's going to show us how to catch Pokemon. And we're going to go to this screen, which looks like the usual battle screen. And there's going to be a Weedle that shows up, and he's going to go ahead and catch it. We actually are in a little bit of a hurry, so we're not going to watch this whole thing. After this tutorial finishes, we need to go to a place called Cinnabar Island. And we're going to use Pokemon's fast travel system. Now, this being the Gen 1 Pokemon games, the way we fast travel is by just turning into a bird and flying off into the distance. Once we get there, we need to go onto these water tiles. And again, this being the Gen 1 Pokemon games, we're going to do that by transforming into some sort of seal thing. I don't know. The 90s were weird. We're going to go up and down this coast, and eventually we will get an encounter with the wild Pokemon. Now, if you play these games, this pause right there is way longer than it normally would be, and we'll get into that more later. Now, here we see our friend Missingno. It's level 168, which is far higher than you're supposed to be able to encounter in the game. The highest level you can encounter normally is 100. We immediately run away, and I'm going to open my inventory and go down to the 6th item, which had rare candies, and I have flower 2 of them. I had 4 rare candies before doing the glitch, so I guess the flower is how it renders 13, because this glitch just gave me 128 rare candies. 128 plus 4 is 132, so 13 is flower. Who knew? Now, if you've never seen this glitch before, this probably seems like an extremely random sequence of events for such a specific outcome. And it is. But we'll break down each piece of this. As with most major glitches, there's no single bug that's responsible here. This happens because of a bunch of different bugs, and in most cases, you can't even really call them bugs, just properties of the code being used in unexpected ways. Now, I do want to state up front, I did not work on this game, nor have I interviewed the programmers who did. But I have spent a lot of time looking at disassemblies of the game, and I think we can infer a lot about what the intent of the programmer was from looking at the code. And we also know a lot about the constraints that they worked under. But I do want to make it clear that a lot of this is speculation. So with that out of the way, let's start going through each of the pieces of this glitch. The first thing you might be asking is, what's up with that weird coast tile? Why do we go there specifically? So this is what a tile that the player occupies in the game looks like. The game works on a sort of grid system. The player can go one tile to the left, right, up, or down. This is what that tile looks like when we remove the player. This isn't how the game views the world. The game actually views the world at a little bit higher resolution. And one tile that the player occupies is actually 4 subtiles. For the middle tile, where the player would normally be, these are the coordinates of those subtiles. The upper left corner is 8, 8, and the bottom right corner is 9, 9. Now, to understand why these coast tiles are so important, let's look at the code, or at least a Ruby equivalent of the code that's responsible for determining if you run into a wild Pokemon or not. So this is certainly not the code. The Game Boy game was not written in Ruby. It was written in assembly, but I have translated to Ruby here to make it a little bit easier to read. The first thing that we're going to do is we're going to load up that bottom right tile that the player is standing on. We're going to assign it to the tile variable. And then we need to get the encounter rate, the percentage chance that we have to run into a random Pokemon each step. If the tile is a grass tile, we're going to grab the grass encounter rate for the current area. If it's a water tile, we're going to grab the water encounter rate for the current area. Otherwise, we're just going to exit out because the player cannot encounter a wild Pokemon. Then we're going to actually do some math and determine if a wild encounter occurs. I've commented that out here because it's not super relevant to the glitch. Then we're going to load up the tile that the player is standing on again. But this time it's going to be the bottom left subtile instead of the bottom right subtile. And then we once again check to see if it is water. And if it's water, then we're going to pick a water Pokemon for the current area to encounter. Otherwise, we're going to pick a grass Pokemon. Now, the bug stands out pretty clearly here. We are loading tile twice, and when we are determining if an encounter can happen, we look at the bottom right subtile. But when we're determining what Pokemon we run into, we look at the bottom left. So whenever we're on a tile like this, where the bottom right is water and the bottom left is land, as we're going up and down this coast, the game is continuously doing these calculations, thinking that we can encounter a Pokemon because of the water, but then when we get an encounter, we'll encounter a grass Pokemon because of the land. Now, this bug stands out like a sore thumb when I translate it to Ruby. The thing is, Ruby isn't assembly, and we lose a bit of important context when we translate this code to Ruby. This bug stands out in the Ruby code in part because I can show you these two lines on the same screen. They're relatively close together. In the assembly, though, this commented out bit of code is actually a heck of a lot longer. And these two lines are more like 50 lines apart. You wouldn't see them at the same time. And that detail alone is a reason to me that I could see this slipping through code review. If I can't see these two lines next to each other, I don't know that I would have spotted this bug. There's an additional piece of important information, though. Because in Ruby, we wouldn't ever assign tile twice. We already assigned it up on the first line. Why would we need to load it up again? And in Ruby, we could just have however many variables we want. The VM just handles where those get stored for us. But in assembly, it doesn't quite work like that. In assembly, things get stored either on the stack or in a register. There wasn't really anything that was equivalent to the heap in Ruby on this Z80 assembly that the game was written in. They did store things at very specific addresses in memory, but that's really not useful here for these sort of throwaway calculations, these local variables. They could put things on the stack, but their stack was only 207 bytes, which is absurdly tiny. So they pretty much only ever used it when they absolutely needed to. The audio playback subroutines were a good example of this. So for the most part, when you needed what you would use a local variable for in Ruby, you would need to put something in a register. And a register is sort of like a global mutable variable for your CPU. You have a limited number of them. And for the Z80, they had, depending on who you ask, 7, but 3 of those had very specific constraints about how they could be used. So really, you only had 4 registers that were 100% general purpose, where you could just use them for anything. And could you write your whole program with only 4 global variables and not introduce bugs like this? I certainly couldn't. Okay, so we can encounter grass Pokemon when we're on these water tiles, but how is that useful to us? We don't just want to encounter random grass Pokemon, we want 128 rare candies. So we need to go further and pair this bug with something else to help us exploit it. So next, let's look at the code that runs when you enter a new area. We had that variable that I referred to in the last set of code called current area, and that gets modified a few times. Whenever we switch areas, we're going to go to some global section of memory where all of the grass encounter tables are stored. This is the list of the percentage chance that you have to run into a grass Pokemon and all of the Pokemon you can run into. So we're going to grab the rate for the area with our current area ID. And then we're going to check if it's greater than 0. And if it is, then we copy that whole table over to the current area's grass encounter table. And if the grass encounter rate is 0, for example, because you're in a city or an area that is only water and there is no grass, we just don't do anything. Whatever was stored there before will continue to be stored there. That's why we specifically do this on Cinnabar Island. Because we can fast travel to any town, it's easy for us to get to this coast in particular without ever passing through an area with grass Pokemon. And as long as we go to one of these coast tiles without entering a zone that has a grass encounter table, we'll just keep whatever was there. And this was really useful. There was a specific spot in the original Pokemon games called the Safari Zone, where there were some really valuable Pokemon to catch. But it used its own special encounter mechanics, and everybody hated it. And people would have loved if we could just use the normal encounter mechanics for those Pokemon. And with this bug, you can. You just go into the Safari Zone, the grass encounter table for the Safari Zone gets loaded up, and then you fly to Cinnabar Island. And on these coast tiles, you can catch Safari Zone Pokemon. And this was called the Fight Safari Zone Pokemon glitch. And that was really useful and became pretty widespread. But that's not enough for us. We don't just want Safari Zone Pokemon. We want 128 rare candies. So if we're going to do that, we need to go even further and have some data in the grass encounter table that isn't a real grass encounter table. Now, when this bug was first discovered, it actually wasn't performed the way that I demonstrated it to you. It was done by going to an NPC trainer, a non-player character, and trading Pokemon with them. The game had a mechanic where with your friends, you could give them a Pokemon and you would get a Pokemon in return. And throughout the game, there were several NPCs who would trade with you, so you could still do this trading mechanic even if you didn't have any friends, like me. Now, for some reason, every single NPC that you could trade with was called Trainer and just Trainer. They didn't really have names. And when you go into a trade, they need a place to store the name of the person you're trading with. Now, they reused a lot of sections of memory in the game, and they end up storing this in the grass encounter table. Now, understand what all of this means. Let's look more concretely at how a grass encounter table is represented in memory. The grass encounter table for the current area that the player is in was stored at memory address D887. Everything on the Game Boy just had very specific memory addresses, and this was the memory address for the grass encounter table. The first byte was that rate. how likely the player is to run into a wild Pokemon. The lower the number, the more likely they are to encounter a Pokemon every time they take a step. Then we had 20 bytes, a series of pairs for each slot in this table. The first byte was the level of the Pokemon you could run into, and the second byte was the ID of that Pokemon. And each slot corresponded to a specific percentage chance of encountering that Pokemon. The first 2 slots were about 20%, the next slot was about 15%, the next 3 were about 10%, and so on and so on. So let's look at what happens when we look at the grass encounter table for a real zone. At the address CFA3, you will find the encounter table for a real zone in the game, Mount Moon. So when we start copying this over, we copy over the byte 10 first. That means we have a really high chance of encountering a Pokemon. And then the first 3 Pokemon you can run into are all Zubats. And then A9, looks like a rocky Zubat to me. And then once we finish copying this over, you might notice something interesting about this grass encounter table. It's all Zubat. I don't know. I guess the developers were like, hey, maybe we should put some Pokemon here. And they were like, oops, nope, all we've got is Zubat. And then kids would just walk through this area, and every 3 steps they'd run into a new Zubat, and they'd go to sleep, and they would just be haunted by these hordes of Zubat. And actually, I'm sorry. Can y'all hold on for just 1 second? Hey, have you not seen the news? There's a pandemic going on outside. Come on. Thank you. Zubats, I swear. All right, where were we? So once we finish copying over the encounter table for Mount Moon, we have, just a lot of Zubats. Cool. So now let's look at what happens when we copy over the name trainer. Because whenever you perform a trade, the name of the person that you're trading with gets stored at the same address in memory. So Pokemon Blue had a really interesting text encoding where there was a control character for print the word trainer. So trainer was actually just a single byte. Names were always 11 bytes, so the rest of this name is just 80, the end of name control character. And that happens to map to Missingno. And so this was a really cool way to do the glitch, because you would end up with an encounter table that was all Missingnos, level 80 Missingno to be specific. Trainer gets copied into the word trainer gets copied into the encounter rate, and that just ends up getting ignored because we use the water encounter rate anyway because of that other bug that we looked at. And so this is a really useful way to perform the glitch. There is a trainer in Cinnabar Island that you can trade with to get this encounter table. The issue with doing it this way is you can only do that trade once. So you can encounter Missingnos right after doing the trade, but then as soon as you go into an area with grass Pokemon, this is just lost forever. You can never trade with that trainer again. So you can get 128 rare candies, and that's all well and good, but we want even more. We want infinite rare candies. Rare candies are delicious, and we want to be able to go get them whenever we want. So the final step to get our rare candies whenever we feel like it is called the Old Man glitch. It's called the Old Man glitch because, well, his name is Old Man. You can see it. It's printed on screen. The fact that his name is Old Man actually isn't important. What's really important here is that he has a name. Everything about Pokemon was optimized for code size above all else. They needed their code to occupy as little space on the cartridge as possible so that they could fit on a smaller cartridge. If your code was too big, you would need to double the amount of ROM on the cartridge, and that was expensive. When Pokemon was originally being written, they just didn't have the budget to do that. So while if you were writing this today, you might have this tutorial just go through a dedicated piece of code for doing the tutorial, if you care more about code size, you can do it much more easily by just adding a few conditionals to, hey, if this is the tutorial, reject player input here. And because they're going through, and that's exactly what they did. This is just going through the same code as a normal battle. And that means that code gets executed that does things like print out the player's name. But it's not printing the player's name, it's printing Old Man. So that means that the string Old Man ended up getting stored where the player's name was, which means that we need to pick somewhere to temporarily store the player's name. So where did they do that? You guessed it, the grass encounter table. So to demonstrate this bug to you, I set my name to Hi Sean, and let's take a look at what happens when we interpret that as a grass encounter table. So we copy over the H first, and again, that's just going to get ignored, so we don't mind. I is 168, and A is Missingno, or S is Missingno, and then I is again 168, and A is, hey, it's also Missingno. And then we got level 174, it's another Missingno, and wouldn't you know it, my whole name is Missingnos. It's almost like I specifically chose that name because it would make it really easy to demonstrate this glitch for all of you. Crazy. Now, one thing you might have noticed, though, is each of these Missingnos came from a different letter in my name. They have a different internal ID, which is weird because it's all the same Pokemon. So let's talk about what a Missingno actually is. Contrary to what you might think, it's not a single Pokemon. There are actually 39 distinct Pokemon which are called Missingno. And it's not just reading garbage data. Even though its sprite is clearly garbage, it has a well-defined name. It's printing out the string Missingno. It's not like there's a way that you can programmatically say, hey, is this chunk of memory real data or not? If so, print Missingno. Like, this must be coming from some table somewhere where they are explicitly expecting Missingno to be the name of a Pokemon. A lot of its other attributes are well defined as well. Really, only its sprite is actually garbage data. So to understand why some of its attributes are garbage, but others aren't, we need to see how Pokemon are stored in the code. When most people think of a list of Pokemon, they think of the order they appear in the Pokedex, the in-game encyclopedia. Every Pokemon has a number associated with it, and they're loosely ordered in the order that you would encounter them in the game. That's not how they're stored in the code. When most people think of the Pokemon with the ID of 1, they think of Bulbasaur. But actually, the Pokemon with the internal ID of 1 is called Rhydon. In the code, most of the data related to Pokemon is stored in the order the Pokemon were created. The game was originally supposed to have 190 Pokemon, but it shipped with 151. 40 of them were either cut or saved for a later generation, and 1 was added at the very last second. And Missingno is what's stored in the slots where the cut Pokemon were supposed to be. So for the most part, the entries for Missingno are always zeroed out. But there are some exceptions, like its name. So for anything that's ordered by internal ID, we're going to get well-defined but zeroed out data. So for example, the list of Pokedex IDs, which is going to be stored in internal ID, Missingno's Pokedex ID is going to be 0. And so because of that, for anything stored in Pokedex order, we're going to get garbage. And let's look at why. So I've got a global variable here called mon data, and that's what's called a Pokemon base stats table. And this includes a pointer to where the sprite is stored on the cartridge. And this is an example of something that's stored in Pokedex order. So like I said earlier, the Pokedex ID for Missingno is 0. So the game needs to look up what a Pokemon's Pokedex number is from its internal ID. Now, we need to convert that from this Pokedex ID to an actual index in an array. And since the Pokedex starts at 1, we need to subtract 1 from that. Now in Ruby, of course, this would just give us -1 because we don't have concrete integer types. We just have our magic number that does very lovely things to keep us from encountering bugs like this. But in assembly, this was a 1-byte unsigned integer. And so when you subtract 1 from 0, you get the maximum value for that, which is 255. And then the array that we're indexing into only has 151 entries in it. Now, again, in Ruby, this would just give us nil because Ruby does a lot of great things to make us never have to worry about bugs like this. But in assembly, that's just not how it works. So instead of getting nil back, we just get whatever was stored after the end of this array. And that's a bug known as a buffer overrun. It's one of the most common memory safety security vulnerabilities out there. In the case of the data that has the sprite for Missingno, the place that in memory that it ends up reading is the middle of the data for some NPC trainers parties on Route 17. And when you interpret that as a pointer, it points to some random code that's related to how the Safari zone works. So that glitch sprite that you see for Missingno is what happens if you interpret that code as an image. But most data isn't stored in Pokedex order, so we get mostly valid data. And ironically, the Pokedex itself is one of the things that's not stored in Pokedex order. It's stored in internal order. So Missingno even has a valid Pokedex entry. Well, almost. Its entry wasn't localized, and the structure is slightly different than the Japanese version. So we can see the height and description are valid, but then it's got like a random number for weight. The structure in the international version for these was slightly different than how they structured it in the Japanese version. So when it wasn't localized, it just gets interpreted wrong. But if we look at the Japanese entry, we can see there's valid data here. Missingno is the question mark Pokemon. It has a placeholder, height and weight, 10 kilograms, and the height is 10 decimeters. For some reason, they stored height in decimeters. I don't know. And that comment translates to comment to be written. Now, for the most part, Missingnos all have the same data. They just have zeros. But there are some differences between the different Missingnos. In fact, a bunch of them have unique data. 9 of them have cries, the sound that a Pokemon makes when you first encounter it, that aren't zeros. A few of these entries also had real sprites associated with them. There were some special cases throughout the game where they needed to show Pokemon sprites in the place where they would normally show a real Pokemon, but the sprite they wanted to show wasn't actually attached to any real Pokemon. So they used a few of the Missingnos to store that information. These versions of Missingno would only show up if you had a lowercase w, x, or y in your name, though, so most people would never see them. But that's a really important detail, is which versions of Missingno you could see and how you would encounter them were based on your name, because your name is what's getting interpreted as that grass encounter table to make this glitch possible. This is also why, depending on what your name was, you might have seen high-level real Pokemon in addition to Missingno. All of the printable characters in their text encoding start at 128, which is the opposite of ASCII and every modern text encoding we use today, where the first 128 characters are what's printable. But that meant that no matter what your name was, the characters that ended up in the spots for Pokemon's level would always be higher than they were supposed to. And depending on what your name was, the characters that were in the spots for ID might have mapped to Missingno, or they might have mapped to Oddish or some other real Pokemon. You could also get some weird glitched out trainer battles with this glitch, but those only appeared if you had punctuation in your name. So I don't think very many people were aware of that. I had no idea until I started doing research for this talk. Now you might be asking, if the encounter table was based on your name, why could everybody do the glitch? Surely it must be possible to have a name that didn't map to Missingno at all. And this is sort of true. It was possible to have a name that didn't include Missingno, but even if that was the case, you could still get 128 rare candies. And it was pretty unlikely for you to have a name that didn't include Missingno for a couple of reasons. The first is that the control character that was used for end of name, which is stored as 80 in decimal, that was one of the IDs of a Missingno. So if your name was an even number of characters, you could always encounter a Missingno no matter what. Because if your name was an even number of characters, the 80 that was the end of your name would end up in the slot for a Pokemon's ID. But a lot of players didn't even pick their own name. They just used one of the preset ones that were offered to you. And by pure luck, every single one of those names had the right characters for Missingno. So if you used one of the preset names, you wouldn't be able to encounter Missingno. And it wasn't even really luck, though, because the characters for Missingno were really common. They included things like uppercase S, H, and M, and most of the lowercase vowels. So the odds of you having one of these characters in the right place were really high. But even then, there was a catch-all. Every custom name could at least encounter Missingno's sister Pokemon, Tick M. And we call it Tick M because those are the only characters in its name that you can actually say. Now, even though Tick M and Missingno have the same sprite, Tick M is different. As you can probably tell from the weird characters in its name and its decision not to wear a mask, everything about Tick M is garbage. The graphics that appear in its name will change based on things like your party's stats or your position on the map. Tick M is what you get for internal ID 0. So you're going to get garbage data even for data that isn't stored in Pokedex order, because no matter what, you will get that underflow. Tick M had a few interesting differences from Missingno. Its cry will randomly change based on what screen you're on, since it's reading some random piece of memory, not zeros. It could also evolve into Kangaskhan, so I guess this is what a baby Kangaskhan looked like. You could also lock up your game by catching it. But if your goal was just to get your 128 rare candies, it didn't matter if you saw Missingno or Tick M. The end result was the same. So let's look at why this duplicates items. Why just running away from these Pokemon will cause the 6th item in your inventory to get duplicated. This has to do with what happens after you encounter a Pokemon. This all has to do with that Pokedex that we mentioned earlier. Its function in the game is to keep track of every Pokemon that you've seen or caught. Any Pokemon that appears on this list is one that you've seen. A little ball icon next to its name means that it's been caught. This gets stored in memory as a bitmap, which is kind of like an array of Booleans, but instead of taking up 1 byte for each entry, it only takes a single bit. So 1 byte can hold 8 Booleans. As you might have guessed, this array is stored in Pokedex order. So when you encounter Missingno, we have that underflow, and so the 0 turns into a 255, and the end result is that the game tries to mark that you've encountered a hypothetical 256th Pokemon. But since there are only 151 Pokemon in the game, this ends up writing past the space that they used to store which Pokemon you've encountered. Immediately after your Pokedex data in RAM is your inventory. Because there are 151 Pokemon, that means that you have to round that up to a multiple of 8 to get to a number of bytes. So the number of bytes, the place that they end up writing is the 13th byte after the end of your Pokedex. The way the inventory is structured is there's 1 byte for the number of items that in your inventory, followed by 1 byte for each item's ID and 1 byte for its quantity in alternating pairs. So that 13th byte ends up being the quantity of the 6th item in your inventory. So another way of saying it sets the high bit of the 13th byte after the end of the Pokedex. An easier way to say that is it adds 128 of that item as long as you had less than 128 before. If you'd beaten the game when you did this glitch, you would also find that the place where it stored the team that you beat the game with, known as the Hall of Fame, was now corrupted. This is caused by Missingno's sprite. Remember when I pointed out the pause at the start of the fight was abnormally long? This is why. Because of the amount of space they needed to deal with sprite information, sprites get decompressed on the cartridge's storage, not on the console's memory. The space that they used for this is large enough for a 7x7 sprite, which is the largest that appears in the game, but the data it tries to read for Missingno's sprite says that it's 13x13. So this ends up giving you that characteristic stair-step pattern that Missingno has, and it writes way past the end of the buffer that was intended for this subroutine. And when they go way past that, they go overwrite the Hall of Fame. Now, because Missingno's sprite is reading from ROM, not RAM, it's reading from code on the cartridge. This means that the data it was overwritten with was consistent for everybody. Although the data that would write would do things like put the control character for print the player's rival in the name. So like a lot of people would see an Ammonite named Gary, but Gary was just a very common name for a rival. It could be anything. Now, this bug would have been avoided if there was some bounds checking in the sprite decompression. But again, everything in this game was optimized for code size. If you're only dealing with a known set of trusted inputs, the real sprites for the real Pokemon, omitting those bounds checks seems perfectly reasonable. The only reason this code misbehaved was because of an unrelated bug that caused it to start getting garbage data. But when this subroutine got a real Pokemon sprite, it always behaved as it was supposed to. Now, those are the only two abnormal effects of the encounter, but there's some misinformation around there. This glitch spread through word of mouth primarily. That means that a lot of false rumors or half-truth rumors spread around. So I'd like to address a few of those. The biggest piece of misinformation you probably heard was don't catch Missingno or it'll corrupt your save. And this is just straight up false. There's no reason that you can't catch a Missingno. There's nothing about it that can't be saved normally. I think the source of this misinformation is a very specific problem that can arise with TickM. In the games, you can bring up to 6 Pokemon with you in your party. And if you catch another one, when your party is full, it gets sent to storage. Whenever you open up the storage system, the game has to recompute all of the stats for the stored Pokemon. And there's a bug in this calculation that will cause an infinite loop if it tries to compute them for level 0 Pokemon. And since everybody with a custom name could encounter a level 0 TickM, and it probably went to storage if you caught it because you most likely had 6 Pokemon by this point, I think this was the source of that rumor. Another thing you might have heard is that catching Missingno will cause all sorts of graphical glitches, and Nintendo even put out an official statement saying to try releasing it to fix the scrambled graphics. And if that doesn't work, you need to restart your game. And just all of that is nonsense. There's this very specific mirroring effect you can cause if you view the stats screen for Missingno. But this only affects a specific sprite, and it goes away if you view the stats screen for any normal Pokemon. There were some bigger glitches if you had a Missingno in the follow-up game Pokemon Yellow, but the glitch that let you encounter Missingno in the first place was fixed in that game, so I don't think that had anything to do with this rumor. Finally, encountering Missingno wouldn't save your game. I'm really surprised this rumor even exists because it's so easy to verify as false. You just load up a save and go run into one and reset without saving, and you'll see, no, it did not save your game. I think the source of this one was an N64 game called Pokemon Stadium. It had an emulator that included the early Pokemon games, and it displays saved on screen whenever anything was written to the cartridge's storage. So when that buffer overrun happened and the Hall of Fame gets corrupted, I think that would make the word save appear on screen. And so that was maybe the source of this, but that would only happen if you were playing on the N64. Now that we've seen every piece of this glitch, we can see that it was just a bunch of really small, seemingly benign interactions between unrelated bits of code. No individual piece of this glitch stands out to me as insane or something that obviously would have been stopped in code review. When you combine all of this together, you get one of the most famous glitches of all time. But it's not the result of some horrendously bad coding or lack of QA. Every piece of this glitch was relatively benign by itself, or was just due to some completely unrelated part of the code interacting with it in some unexpected way. And all this was handwritten in assembly under massive space constraints. Every instruction they wrote mattered. If I had to work under those constraints, I certainly wouldn't have done better than they did. And I don't think any person watching this would have either. A phrase I've heard from folks who make fun of these glitches is completely broken. I think we should just remove that term from our vocabularies. In this case, and many others, it's likely the software was developed under some constraints that we're not aware of, and we wouldn't do better in the same circumstances. These days, it's almost certainly not going to be because of the assembly language that we're working in. It's more likely your company pivoted and you're now trying to salvage this code base to do something completely different, or your deadline moved. Either way, there's always some constraint that leads to these sort of decisions being made. To me, a lot of this glitch just boils down to because assembly. It's easy for us to take the technologies we have at our disposal today for granted. Today, code size is rarely a hard constraint, certainly not for Ruby developers. We don't care how much code we're putting on our web servers, more often than not. In lower level languages, it sometimes matters because of how CPU caches work, but it's really only a thing that you do for very specific optimizations. You're not in 2020 going to be writing a program where this has to be under 20 kilobytes or we can't ship. And we run our code on machines powerful enough that we can use languages like Ruby, which has all sorts of safety checks in it to prevent these bugs, and we just never give it another thought. But in 1996, just use Ruby wasn't an option. Even just using C wasn't an option. I'm glad we don't live in that world anymore. There's a really high quality disassembly of the game, which I used to research this talk. It doesn't have the comments that the real source code would have, but it was an invaluable tool for preparing this talk. If you're interested in how the original Pokemon games worked, I highly recommend checking it out. And a huge shout out to the people who worked on it. I could not have done this talk without you. Thank you so much. My partner co-authored this talk with me. She did a lot of work doing research and on the slides. She's also hopefully going to be giving this at a few conferences. Tess, I love you. Thank you so much for working on this talk with me. It was an absolute blast. I will be around for questions immediately following this talk, but if you are watching a recording of this in the future, hi, person in the future, I hope things are going better for you. Here's my contact info. Please feel free to reach out or send me pictures of Zubats. Thanks.
Yes, as far as I know, yes, we can talk now. So I saw so many Pokemon wearing face masks. I thought we should better.
Yes, Pokemon follow public health orders.
Somewhere at, well, the middle of the talk, no, even earlier already, I thought, how the hell did you get to the bottom of this, which you shared at the very end? Thank you for that.
Yeah, the disassembly was really, really important. It doesn't have everything that the code would have, but you can still get a lot of useful information from it.
Yeah, clearly. And I think, well, you ran somewhat over your slot, so we don't have a lot of time for Q&A.
Oh, I'm so sorry about that.
At least I'm very happy for you to point out how happy we are that we get to use high-level languages.
Yes, yes. Ruby is amazing, and I'm so glad we get to write in it. Yeah, I'm so sorry that I went over time and we don't have time for questions, but please reach out on Twitter if you have any. I will be happy to answer them, or I will be in chat also.
Yeah, so keep an eye open for chat and clearly on Twitter.
Great. All right. Well, thank you so much for watching, everybody.